this this thing equals to right hand side of A, which is equal to ls square by 2 eta mu I phi times del sigma of sigma minus sigma prime. And now I can very easily, comparing these two, this implies to me alpha mu n, alpha mu n, this could be summarized as eta mu nu times m times so this is the result that we would arrive at by simplifying this. Okay, so this leads us to a very wonderful result that alpha mu m, alpha mu n is equal to this. Okay, and this factor eta mu nu sitting here plays a crucial role, because this would then imply the presence of existence of states with negative norm. Okay, and that we would try to remedy. So in the open string case, you see alpha and beta are related to each other. Alpha mu nu is equal to plus or minus of beta mu nu. However, in closed string case, alpha mu nu and beta mu nu are, they stay different. And so for the closed string, you would have additionally beta mu m, beta mu n. This would also be the same, and of course you will have additional results that here for, so this is for open string, for closed string this and this both plus alpha mu m and beta mu n, they would have 0. Okay. In addition to all this, so these would be these are the covariant quantization results for the open string theory, this, and for the closed string, this and this, along with this and this, alpha and beta. In addition, you can also always, for in both the cases, you can additionally have this equals to I eta mu nu, and that would complete so x nu would be 0, p nu would be 0. These are the center of mass of the string, center of mass coordinate of the string, and this is the momentum of the string that we talked about in the Fourier expansion modes of the x nu. Okay, good. So that means we are now happy to have these results. You could do this in all these 4 cases, but the only result that you obtain would be these. Okay, so these are we are quite happy with these results, and we have to try to see. So now I can remove this. Okay, these results lead us to these results, and now we can try to look at the Virasoro constraints and the Virasoro algebra. So I think we could even remove all this. So we need to recap that we have already derived del plus x mu to be equal to Ls by root 2 and equal to minus infinity to plus infinity alpha mu n e to the power minus in sigma plus, and let me write the other one. Maybe I removed it. So do I maybe I should have written them here. Del plus x mu was square root of 2 minus infinity to plus infinity alpha mu n e to the power minus in sigma plus, and del minus x mu h Ls by root 2 summation over n from minus infinity to plus infinity beta mu n and e to the power of minus in sigma minus, and here this n is a this n is a real number, and here we have included n equal to 0 term is included in both. Okay, in both of them n equal to 0 term is also included. Okay, if it suits us, we can take it out and play with it. So now we would like to develop the, we know the 0 equal to t plus plus, this is del plus x mu whole square. This is one of the constraints that the t plus plus component of the energy momentum tensor vanishes, and this could be written as Ls square times 1/2 alpha n scalar product in the D space e to the power minus im plus l sigma plus, and here L and M, they go from minus infinity to plus infinity. And so what are we doing here? What we are doing here is you take del plus of x mu and take its scalar product with another del plus of x mu. Once we write del plus x mu with some number L, and another time we write it with M. So this is just a scalar product of these two. Okay. So the scalar product of these two could be written as this, and this here could be written as Ls square summation of 1/2 n minus m and m times e to the power minus in sigma plus. So what we are doing, m plus l, we put it equal to n, then L is equal to n minus m. So you can replace L by n minus m. Okay, we can replace this L by n minus m. Okay, this is what we have done. And here now we can define, I think we can remove this now. So we could write it as ls square and summation over n and ln e to the power minus in sigma plus here ln is equal to summation over m 1/2 n minus m and m. I could equally write it as ls square summation over m ln e to the power minus in sigma plus where ln is summation over n. I have somehow, while writing my notes, I decided to work with lm, and therefore I have just rewritten the same expression. Instead of n, I have written it the same expression in terms of m, but they are equivalent, right? Here you have summation over m, here you have summation over n, so this m index is free. Okay, just the equivalent